You build a Retrieval-Augmented Generation prototype in a local notebook. It answers your test queries perfectly. You deploy it to a live production environment, and within a week, the system breaks under real-world load. This is the just add RAG fallacy. It is the widespread industry assumption that simply connecting an embedding model to a document corpus and an LLM creates a production-ready system. That three-step pipeline works for a weekend tutorial, but in mission-critical applications, it degrades into a black box that confidently generates false information. Building reliable AI requires stepping away from simple API calls. Success depends on rigorous, deterministic data engineering. Real-world RAG demands a different architecture, a multi-stage pipeline governed by strict mathematical gates. To build it, we overhaul 3 layers: ingestion, search algorithms, and the evaluation framework. If any layer remains naive, the language model receives corrupted context, producing unpredictable, ungrounded outputs. Reliability stems from the mathematical control exerted over input data, regardless of the parameter size of the language model. The ingestion pipeline is the silent killer of RAG systems. If context is destroyed here, the language model cannot recover it. Default ingestion uses fixed-size chunking. A medical document is sliced by character count, regardless of meaning. This physically severs a critical warning from its procedural step. When queried, the system retrieves this isolated fragment. Lacking surrounding context, the LLM guesses the missing information, causing hallucinations. The enterprise-grade solution is semantic chunking. Instead of arbitrary limits, the system analyzes the document structure, dividing text along natural boundaries like headers, paragraphs, and logical concepts. This groups information into coherent idea blocks, preserving the original metadata and structural hierarchy of the source material. This ensures the vector database is populated with complete, standalone concepts rather than broken mid-sentence fragments. If ingestion fails to preserve semantic context, the entire retrieval pipeline operates on corrupted data, rendering the final output inherently untrustworthy. Once data is cleanly ingested, you face the retrieval challenge, surfacing the exact right chunk out of millions to fit the language model's context window. Most systems rely on dense vector search. A search query maps into a vector space, finding a cluster of semantically similar chunks, but completely bypassing the required ID number. Dense retrieval understands broad intent, but frequently fails at exact term matching for specific IDs or acronyms. To fix this, you must introduce sparse retrieval, specifically BM25 keyword search. This runs parallel to your semantic search, scanning the document corpus for exact keyword overlaps. Executing dense semantic pathways and sparse keyword pathways together is known as hybrid search. This creates a core engineering challenge, merging 2 distinct mathematical ranking lists into one coherent set of candidates. The mathematical solution is reciprocal rank fusion, or RRF. This equation calculates a new rank for each chunk using combined inverse scores. By neutralizing individual algorithm biases, RRF ensures chunks scoring well in both semantic meaning and keyword density rise to the very top. Relying on a single retrieval method guarantees systemic blind spots. Hybrid search ensures both semantic meaning and factual precision survive the retrieval phase. Hybrid search provides a combined pool of 20 to 50 candidates. That is still too noisy for the language model. Language models struggle to utilize critical facts if buried in the center of a massive text block. This is the lost-in-the-middle phenomenon. You need a final retrieval gate, the cross-encoder re-ranker. This node scores each retrieved chunk against the user query. While initial algorithms calculate similarity independently, re-ranking models process the query and document together end-to-end, executing a deep relevance check to push best matches to the top. This 2-stage approach provides the speed of initial retrieval with the high-fidelity precision of a careful final selection. Without a re-ranker, the language model is easily overwhelmed by mediocre context. This filter maximizes the signal-to-noise ratio before any text is generated. Once the pipeline is built, performance must be measured. In a production environment, manual testing and vibes-based assessments are unacceptable liabilities. The industry standard for continuous testing is the LLM as a judge paradigm, using reference-free evaluation frameworks like RAGAS and TrueLens. These tools use the RAG triad, mapping interactions between user query, retrieved context, and generated answer. First, context precision verifies the most relevant chunks sit at the top. Second, faithfulness extracts claims from the answer, cross-checking them against the context to ensure all statements are entirely grounded. These metrics run autonomously inside CI/CD pipelines as automated regression tests. Integrating deterministic evaluation allows teams to block code deployments that degrade faithfulness. This makes hallucination prevention a hard engineering gate. The final architecture prioritizes stability over simplicity. The optimized pipeline includes semantic ingestion, flowing to hybrid search, filtering through cross-encoder re-ranking into generation, all enveloped by an active evaluation telemetry loop. Success in RAG depends on data engineering and search optimization. Enterprise AI requires total control over context, retrieval, and evaluation. Managing these stages makes RAG a mathematically reliable business asset.